It's like, he keeps killing me. It's just like, I'm reported for terrorism.
Wait, Hunter reported him for terrorism?
Because Xbox, okay, what thing you should know about Xbox is they don't actually like ban you unless you like specifically
Unless
do
you're
something
me.
really bad. So like they don't even check the report. So like you can report someone 800 times for terrorism and Microsoft would be like, oh well, I fully intend.
Terrorism.
Okay, let me pull up one thing right quick.
I have to go look at, I think I still have the Xbox app on my phone, but I got this message from this kid that I beat in Fortnite. He was like 12, and it was him telling them that my mom's gonna die because of me and all this stuff. And I was like, buddy.
Do not ever play Rainbow Six on Xbox.
Don't ever play anything on Xbox. That's why I have a PlayStation now.
I changed my name to I cannot aim on Xbox so that people would stop messaging me about how I can't aim.
I can't aim.
Okay, so okay,
Wait, I'm not here. Email one time, it's like stop reporting people for no
Kelsey.
reason.
all right. So this kind of shows the impact of, speaking of electricity and capacitance and things like that.
Physics, not tax.
So this shows that the solar array feeds into just like the Mace Career Academy. And so when you become an electrical customer, you're going to get, they typically give you a graph like this. So this shows like the net energy usage for the Career Academy over the last year, okay? And so this was March of last year, and then you hit April, May, June, July, August, September. So basically on that whole stretch of months, the Career Academy basically didn't use any electricity at all because the solar array produced basically everything that we needed. Sometimes it produced a little bit more. And then you can kind of see like the impact of temperature and like the shortened days because of, the weather is short, just didn't have as much daylight hour. It was get a little bit colder, so we used more and more electricity. And then you hit March, and March was pretty seasonable, okay, even though we had like some rainy days. It was pretty seasonal, so we only used just like a little bit of electricity. And so if you compare like last month's electrical bill was like, $3,800, and this month's bill was like $1,000. And so typically though, those bills are running, if we didn't have the array, those bills would be running about $3,500 to $4,000. And so it's pretty cost effective. So this is what I'm actually going to take to the Bueller School Board tonight and do a presentation for them about the cost savings and things like that, and go, hey, here's the proof they work. It greatly reduces your electricity bill and pays for itself. So anyway, all right. So here's the drill for today. We need to talk about capacitors. This is kind of the last big thing that we have to talk about. We've mentioned it before, but this is just going to kind of focus on that. And then I got a circuit set up there in the back. So work through some problems with that and kind of show you how capacitors work. And then you've got your last assignment today, and then we'll review tomorrow, and then the test is going to be on Wednesday. Okay? And then we'll start into magnets, and then we've got nuclear left over after that, and we'll go from there. So, all right. So if you look at capacitors, and here's where, and especially once you get into magnetic fields, you have to keep track of E versus like that epsilon, and that's what I was questioning on some of those on that lab that I just gave back. On the battery, it had like that fancy E, okay, which is oh, thank you, which is that electromotive force, which is your voltage. So don't confuse that E with your electric field. So here's where a confusion happens. So if you look at the strength of an electric field, that's the charge on the plates. Here's epsilon naught, which is a vacuum permittivity constant, and this is the surface area in square meters. Now, if you compare that to the value of capacitor, so this is epsilon naught times the area divided by the distance. So here's the difference. Your electric field is inversely proportional to the area, but your capacitor is directly proportional to the area. So here's the deal. With this electric field, if you take that same charge and you spread it out over a larger area, then the strength of your electric field becomes less because it's like more diffuse. Because the capacitor works to store energy, then, and that's fundamentally how that works. So with the capacitor, as your area becomes bigger, then your capacitance becomes bigger. So these two are like inversely proportional to each other. Now, and this is also on your equation sheet. This is also your electric field. Change in voltage divided by R. Functionally, this works by voltage equals ED. Okay? This is the strength of your electric field, and this is typically the distance between the two of them. So this is typically what you're going to calculate, okay, is your voltage. Now, because capacitors act like batteries, okay, the whole function of a capacitor is to store energy, and that's the analogy that you make with a capacitor holding up water behind a dam, okay? So that's why you can't set electric fields that involve energy, okay? It's just the strength of the electric field. But because of capacitors, their ability to store energy, so there's two ways you can calculate this, and this is what's on your sheet. One is the charge, and this is your voltage across the capacitor, okay? And I'll show you that works in just a second. So obviously, if the function of a capacitor is to store energy, and there's no charge buildup on the capacitor, guess what? You're not going to have any energy stored. That would be like, well, how much potential energy does the tennis ball have sitting on the ground? Well, it doesn't have any because there's no energy stored in it. Now, I lift it up, oh, voila, hey, now I stored potential energy. And then also, if there's no voltage across that capacitor, nothing's going to happen there. The other way that if you happen to know the capacitance, okay, and this capacitance is going to be measured in farads, so if you know the value of the capacitance and the voltage across it, then it's delta D squared. So with this one, if you double your voltage, you double your potential energy using this equation. With this one, if you double the voltage, you multiply it by the capacitance, then you're going to quadruple the potential energy stored in it. Okay? So that's what you have to watch on these. Now, the other one that's on your sheet, okay, is that delta V equals Q divided by your capacitance. Okay? This is what's on your sheet. Now, the other thing that's going to happen, and this is the last of the equations that involve capacitance. And this is like the opposite of what happens with resistors. So if with capacitance, if they're in parallel, you just add them together. Now, remember with resistors, if they're in parallel, you add the inverses of them. Capacitors, if they're in parallel, you just add them together. In series, you add the inverses of them, okay? So capacitors and resistors, mathematically, how you find like the equivalent capacitor or the equivalent resistor, they're like inverses of each other, okay? All right, so got this idea. All right, so let's go to the back and I'll show you a circuit. Okay, so this is going to take me a while to kind of get all of this set up and explain what I've got, because that, you all see like the diagrams, they look really, really nice and it's simple, and it's, well, here's the reality of it. Okay, so here's what we've got. So I got 9-volt battery, got it switched, it's feeding into a 1,000 microfarad capacitor. Okay, so the electricity is going to flow here. It's going to go through there into another 1,000 microfarad capacitor that's in series. And then it's going to hit that. Then it's going to go hit a resistor. And then I've got an LED light. So this is like, imagine this is like this interior loop. So it's going to go from the battery to the switch, to the first capacitor, to the second capacitor, to the resistor, to the bulb. Okay? Now, in parallel with that, I've got this outer loop here that starts with this white wire. So it's going to come out here, and it's going to go into this LED light, into that switch, into a blue LED light, and back to this capacitor. Okay? So here's what I want you to think through. So the first thing I'm going to do is I'm going to have that switch open. Okay? Basically, there's nothing's going to happen in the parallel loop. I'm going to throw this switch, and what should happen?
The light bulb, those light bulbs should go on. Or that one, the red one.
This one should go on.
Oh, wait.
It'll blink.
Wait, yeah. Because of the capacitors.
Okay? Will it stay on bright, or will it light up and then go out?
Light up and go out.
Okay. Now, here's the other thing I want to do before I throw the switch. So right now, if I measure that capacitance, okay, so I've got a little I've got a little energy stored there. So what can I do to get rid of the energy that might be stored in that capacitor?
Flip your parallel circuit.
Flip this one, okay? So if I flip this, okay, right? And that's going to take all that energy out, or for the most part it did, okay? I got a little bit of voltage left, but not much. Okay, so I'm going to open that up. I'm going to close this switch. Now, what I want you to watch is what happens to the reading on that voltmeter once I close this switch. So when I close this switch, what do you think is going to happen to the voltage measured on that capacitor?
It's going to jump up
Why?
It'll spike.
because it's going to let a lot of current through it first.
But then eventually, what's it going to do?
Start going down.
Yep. Okay. So I'm going to throw this switch. Okay. Now, notice that went up, right? And then it stayed steady. Look what happened to the bulb. What did the bulb do?
Well,
It lit up and then it
Then
dimmed, right? So what's happened is that I've increased the capacitance. So when I threw that switch, this energy got stored. Now I've got energy stored here, right? So this voltage here is at about 2.5. So now I'm going to measure the voltage across both capacitors. So if I measure the voltage across both capacitors, now I'm up to about 8. Okay? So basically what's happened is that each one of those is storing about half that energy. Okay? So I'm going to open up this switch, okay? And then I'm going to close this one. So then what's going to happen?
it'll blink.
Okay? I'm going to discharge that, okay? Hold on. Let me chunk that back up. So that blinked on, right? So I'm going to open up that, boom, close this one. Okay, those blinked really, whoa, those blinked, whoa, easy. Okay, get a little excited about my capacitors and almost fell on my capacitor. So that discharged that as quickly as possible. My voltage dropped basically to 0. Okay, so that's option number 1. So now I'm going to do this again. I'm going to open this up. Okay, and hold on, let me think this through. No, I'm going to close this one. Okay. And then I'm going to close this one. So then what's going to happen? So I've got this one closed. So now I've got that external loop as a possibility. So now what's going to happen?
Wouldn't it just go through the external loop?
Just going to go through the external loop. Why?
Because the capacitors are extra resistance.
Okay.
I wouldn't want to go through them.
So if I do this, okay, So that energy is flowing out there, but also notice though, I have stored energy in that capacitor, okay? So basically, we took that energy, right? It got filled up very quickly, and then it said, okay, hey, we're done. We're gonna divert that electricity out around there. So if I open this one, okay, notice everything goes out, but now, notice that once I open that, this capacitance goes up even higher, because now it's going to take all of that energy that it had and completely store that in that energy. Okay, so open that, close this, flash of light, boom, energy is going to get dissipated, voltage is going to go down. So these are 100 microfarads that are in series. So now I'm going to change it up a little bit. So now I want to put these in parallel, okay?
So
What?
that light blinks when you put the switch down originally, like the first time you did it, because originally the electricity goes through the two capacitors, and then once they start storing more energy, it just dims.
Yeah,
Okay.
okay. Now, capacitors, when you look at them, they have an arrow. Just like LED lights, your energy has to flow in a particular direction. So let me hope that I got that right. So we'll close the switch. And why are we not storing energy? Here's the problem with these. If you have one loose connection, okay, there we go. So that flipped out very, very briefly. Okay, then we do this. Okay. All right, so okay, let me reset everything now that I know everything is hooked up right. Okay, so I'm going to measure the voltage across here. So this is open, right? So, boom, I spike up. I've stored energy across this capacitor. I've got nothing going on out there because that is closed. I open this, close that, what's going to happen? Flash the light, boom. Okay, should have. Come on, work with me here.
We'll just pretend it did.
We'll just pretend that it did. Which is odd because it should have, because,
So they both blink, the red and the blue?
yeah.
So the electricity just doesn't like to turn.
Yeah. Oh, they all do.
Yeah, they all did. Okay.
And then when they
Hold on.
blink and the switch is down, do they just stay dim or do they
Yeah.
go out completely?
No, well, they should go out completely. Okay, so I must have a loose connection somewhere. But here's, because this should discharge this. Let me circumvent the capacitor. Okay. All right. So when I took out, I think the capacitor had so much resistance it wasn't allowing that to go through. So here's the deal. So if you have them in parallel, okay, you add them like they are, just add them together. If they're in series, it's just like the opposite of what you do with resistors. So they store energy. You can measure that as that voltage across there. The higher the voltage, the more energy that you store. Got it? Good? Grand? Okay, back we go. Thank you. Okay, so let's say we have this scenario here. So you have two capacitors that are in series. Excuse me, that are in parallel. You have two capacitors that are in parallel. So how are you going to find the equivalent capacitance of those two that are in parallel. One's 50 microfarads, the other one's 100 microfarads.
Just add them.
Just add them together, right? So this is like having one 150 microfarad capacitor, okay? Now, you're told the capacitor 2 has twice the capacitance of 1. So if you look at this and turning C equals epsilon A over D, assuming that they have the same distance between the plates, the only way that I can make this one have twice the capacitance is if it has twice the area, okay? So if that had 1 square centimeter, this would have an area of 2 square centimeters, okay? Because that's the only way that you can increase that, is by increasing that area. So if you look at what you can do with this information then, right? So if you look at your voltage, okay? So let's say this is a, I don't know what we just used, like a 9-volt battery. So when you hook them up in parallel, and this is what I tried to show you, is that both of these are going to have the same 9-volt voltage across it. So they're both going to take on the voltage of whatever the battery is. Now, if they're in series, they don't. Okay, in series they would add up to 9 volts. Okay, but if they're in parallel, they're both going to have the same voltage jump. Okay, so that's going to be important. So if you look at this one, so if this is going to be C1, that's going to be like epsilon naught A over D. Capacitance 2 then would be epsilon, oh I screwed that up, epsilon naught 2A over D. So if you look at delta VC, okay, so here's what we're going to look at. So if you just let capacitance 1 be epsilon naught over A over D. So that means capacitance 2 is going to be epsilon naught 2A over D. Okay, we're just going to make it simple and assume that they're separated by the same distance, whatever that is. So if you look at the charge, right? So Q equals delta VC. So since they both have the same voltage, what are you going to know about the charge on each one then?
Same.
Are they going to be the same charge, or is the charge going to be different? Well, look, this is going to have the same same change in voltage, right? So this is this capacitance. So if this one has twice the capacitance, shouldn't this one have twice the charge?
Yeah.
Right?
Yeah.
Okay, because Q equals delta VC. They both have the same voltage. This one has twice the capacitance. This one's going to have twice the charge available to it. So then if you look at this, going, okay, well Q1 is just going to be delta VC. So Q2 is going to be twice that, because that's going to have the same delta V, but it's going to have twice the capacitance. Now, so if you look at, and here's where electric fields become a factor in this. So if you look at electric fields, okay, so electric fields in each one is going to equal Q over epsilon naught A. Okay, so this is how you can calculate the electric field. So look at this one. If you look at the first one on the electric field, that's just Q divided by A, right? Now, if you look at the second one, that's going to be 2Q, so it's going to have twice the charge. But guess what? What about the area? It's going to be twice as much. So even though one has twice the charge and twice the area, guess what?
Same electric
They're
field.
both going to have the same electric field, because one has twice the charge, the other one has twice the area, but the electric field on them is going to be the same. So I screwed that. So E2 is going to equal 2Q over epsilon naught 2A those cancel out. E1 equals E2. Now, that's only if they're in parallel. Now, if you look at energy, so if you look at the potential energy stored in that capacitor, so this is going to be at 1/2 Q delta V. So because they're in parallel, and this is huge, because they're in parallel, they're both going to have the same voltage drop, okay? So if you let this be the energy stored in capacitor 1, that's just going to be 1/2 Q times delta V. But if you look at the energy stored in the second one, that's going to be 1/2 2Q delta V. And the voltages are the same, so what do you know about the energy stored in the second capacitor?
Twice as much.
Yeah, so it's going to store twice as much energy because of the fact that it's going to have twice as much charge with the same voltage. So I point this out because with capacitors, there's a whole bunch of different things that become factors in this. You have to look at area. You have to look at how that impact, what impact that has on the value of the capacitance itself. What does that have on the electric field? What does that have in terms of energy that you're going to store? Okay, so that's why capacitors get sketchy, just because they work pretty simple, but in reality, because of, you can look at electric fields, you can look at energy, you can look at charge, you can look at a whole bunch of different things. So that's why it's important that you keep track of what are you going to hold constant and what are you going to change when you're comparing those. Okay. Now, last one. So let's say that you're going to have, let me scoot that up. Okay, so let's say that you have two parallel plate capacitors. One is 10 centimeters on a side, and that's separated by 4 millimeters, which is about like yay, okay? The other one has 5 centimeters on the side, but it's only separated by 1 millimeter, which is, about the thickness of a human hair, roughly, okay? Actually, that's bigger, but you get the idea. So I want to compare the capacitance on each one. So what are you going to have to know? So capacitance is going to equal what? Epsilon naught times
A over D.
divided by D, right? So we'll call this one 1 and we'll call this one 2. So, Diego, you're going to go 1 over 2 or 2 over 1? Okay? So this is going to be epsilon naught, and that's going to be 25 centimeters squared divided by 1 millimeter. Now, I'm just going to leave those as centimeters and millimeters because all I'm doing is a comparison. I'm not actually calculating the value of the capacitance. Okay? It's not what I need. And then this one's going to be epsilon naught. And then I'm going to have 10 centimeters squared divided by 4 millimeters. Okay? Well, the epsilon naught's going to cancel out because I'm not actually finding the value of the capacitance. Okay, that's not what I need. So if I take 25, right? Or excuse me, that's 5. Let me back up. I already, never mind. That's 5. It's 5 squared. I was one step ahead. It's 5 squared. So if I take 5 squared, I get 25 divided by 1, right? And then if I take 10 and square that, I get 100. I divide that by 4, I get 25 to 1. So guess what? What's the ratio of their capacitance? Yeah, it's still a 1-to-1 ratio. Even though, so here's your trade-off. So the first one had 10 centimeters by 4 millimeters, right? Okay? So that had a bigger area, but they were further apart. This one had a smaller area, but they were closer together, okay? And because of and if you notice, because your area is squared, and hopefully by this point, kind of in your ability to do physics, you go, oh, something's squared. Well, look. So this is a 4-to-1 ratio based upon distances. This is a 2-to-1 ratio of areas, but the area gets squared, so that's why it still works out to be a 1-to-1 ratio. Okay? Because this is area and that's squared, so even though this is doubled, but you square it, oh, that's a difference of 4. This is a difference of 4, therefore it still works out to be a 1-to-1 ratio. Now, if you actually wanted to calculate the value of the capacitance, you go, okay, well, what is the value of that capacitance? So if you're actually going to do that, now when you look on your sheet, this is what's actually on your sheet. I'm going to write it as it is on your sheet. So this K is called the dielectric constant. This is what you want the test. This is what you will actually see when you go to calculate capacitance. This dielectric constant, it's there, and I have never seen it be anything but 1. Okay? And they would actually have to specifically tell you that the dielectric constant is something other than 1. Okay? So just ignore it. So you got your area. So Amanda, which one do you want to do? The first one or the second one? Okay? Now, we need the value of epsilon naught. So what's the value of epsilon naught?
8.85.
What'd you say?
8.85 times 10 to the negative 12.
Times 10 to the negative 12, right? And then your area, now, because we're actually calculating this, okay, so this area has to be in meters. Amanda, which one did you want to say, the first one?
Yeah.
Okay, so that's going to be 0.10 meters squared, and then 4 millimeters. Okay, so we got 4 millimeters. How many millimeters are in a meter? 1,000 millimeters. So somebody take 0.1 squared and then divided by 0.004 times 8.85 times 10 to the negative 12. And you're going to get a really, really small number.
2.21 times to the negative 11.
2 point what?
21 times to the negative 11.
Farads. Now this is where if you want to get fancy and you want to play the numbers game, you can, okay, in terms of like prefixes, okay. This is why you get into like, that's why a 1 farad capacitor is actually really, really big. Most capacitors are really, really small, okay? Because if you look at the only thing that you can do, you're starting off with a really, really small epsilon naught, the vacuum permittivity constant. So this is really, really small to begin with, okay? So to get any kind of large capacitance, you got to have a really, really big area and then separated by a really small distance, okay? And if you did the math with the other one, oddly enough, you would still get 2.21 times 10 to the negative 11, okay? All right. So I am done. Now, the reason, well, you got about a half an hour. On this assignment, you're going to have questions about bulbs and brightness, okay? So if you're not sure, and this is where I'm going to give you some more time, pull up that circuit building program and build them, okay? So if you're not sure how to rank these things, take your time, build the circuit, or if you want to, do the prediction, and then see what happens. I promise you on the test, I promise you, there's going to be questions where you're going to have to rank the brightness of bulbs. I promise you, okay? So now, keep in mind on the test, you're not going to be able to say, hey, Bodie, what'd you get? Well, this is what I think should happen. Oh, let's build it on the circuit builder program. Okay? So, right now, you still have access to the circuit builder program. Obviously, on the test, I'm going to say you're not. So, especially when you get into like 12, 13, 14, and 15, with those, actually all the way through 16 on this assignment. When in doubt, what I would do is that I'd try and predict what's going to happen, and then go from there. Now, some of these diagrams, I draw them a little bit hinky. So if you look on, and don't flip out on this one, because you all are used to like right triangles, and some of you deal with this better than others. So if you look on number 14 on your assignment, they've got like a battery like this, and then they've got like a bulb here, a bulb here, a bulb here, everywhere a bulb, and then another one. So they've got like A, B, C, and D, okay? And some of you are like, oh, we've never seen triangles before. How do we deal with triangles? This is bad. Look, it's a parallel circuit, okay? That's it. Don't flip out. It's like, but they're not at right angles. That isn't how you taught us, Mr. Burkamp.
Yeah.
It's okay.
It's not right.
It is literally not right, okay? But it is a right triangle here, if that makes you feel good. I'm trying, man. I'm trying.
It's not your fault.
I know, but I'm just, don't flip out. And then 15's even going to be worse, okay? 15's going to really mess you up, if that did, but not bad. So on 15, you got this one, A, B, C, D, and E. So you've got this coming in, and then that splits into these two, and then you've got this external parallel loop going like this. So if you really want to check out your game, okay, if you really want to check it out. So on 15, all it tells you is that they're the same brightness, okay? Excuse me. They're the same resistance. They're identical bulbs. So that makes it somewhat nice because they're identical. Now, if you really want to test your ability, build the program. I don't care what you set as your parameters, okay? Make this 20 volt, whatever. If you really want to make sure, Adeline, you were listening to me, if you want some extra practice because you still have access to the program, okay? If you want some extra practice, build this and then actually do the computation. Calculate the current at each point, okay? Calculate the voltage drop across each point, okay? Calculate the equivalent resistance in this thing, okay? If you want to actually make sure that you're feeling good about it, while you have access to that program, build it. Make your prediction, see what happens. Now, if you really want to set up some dramatic flare, build it and then have a switch. And then say, go to someone in the room and go, close the switch, I want to see if I got it right, okay? Just for a little bit of added dramatic flair. I'll leave that up to you. Okay, I am done. So here is your last circuits assignment.
Oh, let's pull up 70 through 60.
Yeah, I didn't see that.
Now, some of these questions specifically ask you to explain your answer. Okay, I think like those first two especially. Ask you to explain your answer. So these are the ones where it's like a ranking of brightness. These are all like capacitor problems. But here's what I'm most worried about on the test. I'm not worried about the mathematical computations. You all were great at that. I'm worried about the calculations with the brightness and the complex circuits. That's what I'm worried about. So, okay, I'm done. You're on your own. Again, write down these lines.
Yeah.